Today we're looking at graphs of functions. Some of this stuff, using a vertical line test. Nobody's challenged by that. Finding the zeros of functions. Since this is about graphs, it ought to be not just the solving, because we did that in the last lesson, but there's a little bit of both in there. The intervals of increasing and decreasing. And then relative maximum and minimum values. We'll do that. Average rate of change, and even and odd functions. Kind of, a hodgepodge of things. I think some of them you've already had. Some of them might be new. So first, domain and range. We know what we mean by domain and range. Domain means x values. Range means y values. But in terms of looking at a graph and determining domain and range, this graph here is a quadratic. It's a parabola. It's opening down. When you look at something like that, you're supposed to see that these here are going on forever. Okay. This is going on forever down and forever to the left, forever down and forever to the right. The domain, the x values are, because this is going forever to the left and forever to the right, it's all real numbers, right? All real numbers. Yes, they don't actually give us the function. All real numbers. Right? This is a domain. Now, in the book, the way they'd probably write that is like this, with the interval notation: negative infinity, comma, positive infinity. Means it goes all the way on the left to negative infinity, all the way on the right to positive infinity. Now, the range would be the y values. Well, this parabola is made up of infinitely many points, but they don't go infinitely up, do they? What's the highest point you see on that graph? Right? This point there is the highest point, right? All the other y coordinates for these points are going to be less than 3, and it does go forever down, right? So you would say that the range is what?
Negative infinity, 3.
Okay, if we set it with the inequality symbols, it would be x is less than or equal to 3. If we set it with the interval notation, it would be negative infinity
Like a square bracket on the right.
to 3, and then because it includes 3, you use a square bracket. Okay. Now, maybe I got it here. Oh, there we go. Now, if I go to, again, this is your textbook online, which you might be able to get it. I haven't figured it out quite yet. But if you notice on the inside cover of your, maybe it's the back cover. Yeah, go to the back cover of your book. And they've got lots of functions with lots of, and most of them, they're telling you the domain and the range for that kind of a function. And it ought to match up pretty closely with the graph. I mean, what I find with domain and range looking at a graph is you might have a little bit of trouble looking at it at the beginning, but once you get it, it's like, okay, this is easy. It's not that hard. You need to just look at a lot of graphs. Which book is that? We are on 1.5, right? Yeah, they didn't all work out. But if you could look here, like the linear function, you see when you have a straight line, whether it has a positive slope or a negative slope, that line goes forever up and forever to the right, forever down and forever to the left. So domain and range is all real numbers for all linear functions except for 2. Which 2 don't have domain and range of all real numbers? Vertical and horizontal, right? But all the rest do. Here's the absolute value function. This is the parent function. The domain understanding that this goes forever to the left and forever to the right, the domain is all real numbers. What would you say the range is? Yeah, it goes down as low as y equals 0, and it goes back up again. And they've got it right there. I mean, you can check yourself to see whether you're looking at this thing right. So it's 0 with a square bracket to infinity. That would be y greater than or equal to 0. Here's the square root function. You know, just looking at it here, it starts at 0, 0, and it goes up and to the right from there. So the domain is greater than or equal to 0. The range is greater than or equal to 0, right there. So you can look at these and see whether you can make sense out of them. That's a funny one that I don't know how many of you have seen this one before. It's called the greatest integer function or a step function. You know, it's just a bunch of stair steps like this. And you can see for every x value, like at x equals 1, it's an open circle there, but it's a closed circle there. At x equals 2, it's open circle there, but it's closed circle there. So in fact, you do have all the x values covered. But what is the range? The range is -3, -2, but nothing in between those two, right? -2, -1, nothing in between. The range would just be the integers. So let's see. The range, the set of integers. The domain, all real numbers, right? A quadratic. There's the parabola. Depends on whether it opens up or down. It's always the domain is going to be all real numbers, which if you have the fortune of actually having not just a graph to look at, but the equation, then it gets into the kind of domain we talked about in the last lesson, which is this book called The Implied Domain, right? When you look at this ax squared, there's no dividing, so there's no way to divide by 0. There's no square root, so there's no way to take the square root of a negative number. It's not a logarithm, right? So it's all real numbers, meaning you can plug in anything you want to that function. The range depends on if it opens up or down. If it opens up, y greater than or equal to 0. If it opens down, y less than or equal to 0. So I just wanted to point out, you have a lot of functions to look at that have domains and ranges that you could try to look at and see whether you could make sense of. When I look at some other graphs, we'll use graphs for a lot of reasons in the lesson today, not always for domain and range, but we can always throw that in just because it'll help. Vertical line test. Well, we know how the vertical line test works, right? I mean, we want to know whether a certain graph represents a function. So we draw a vertical line, and what would make it not a function? If it crosses the graph of the function in two places. Now, go back to the definition of a function, right? A function is a relation that has one y value for every x value. So the reason that this works is because if that is a vertical line, at this x value, there's actually two y values, right? That's if you cross in two places, by definition, you just had two values for the same x. That's not a function. A function, we expect one value for the same x. Now, you have to kind of use your imagination because it has to do with if anywhere in that graph you could see a vertical line test failed, then the whole thing fails a vertical line test. This one, vertical line test, pass. But I mean, you have to kind of imagine. It didn't matter where you drew that line. It was going to be that way. What about this one? Really? Did it cross in more than one place? It doesn't have to cross, right? It doesn't have to cross. So that's a function. I mean, for every x value that is in the domain of this thing, it has it. Now, just because we're doing this, notice that, okay, this one is actually drawn on the, that's 1 on the y-axis. What would you say is the domain of this? What x values do all these points have? All real numbers? Does it have values over here? Greater than or equal to 0. What is the range? All real numbers. You would assume that these arrows are going infinitely up, infinitely to the right, infinitely down, infinitely to the right. What about this one? Domain is all real, these arrows, you know, it's just like a linear function, right? It's actually a cubic, but all the odd degree polynomials are all real numbers for the domain, all the real numbers for the range. What would you say is the domain of this one? You're going to need two intervals. This one right here. X values, right? X is less than or equal to 0. X is greater than or equal to 2. What is the range? Y is greater than or equal to 1, right? These stop at a point right there. Okay, use a vertical line test. What do you see? Would you say it's a function or not? I mean, more than that, what kind of a function does it look like? It looks like a quadratic function. That looks like a parabola. We know that parabolas are functions. Parabolas that open up and down are functions. So we can just try to imagine, but it's really only crossing in one spot. So that is a function. Easy stuff. Okay. So finding zeros. The zeros of the function are, and here's the function. What do we mean by the zeros? The x values for which the function equals 0, for which f of x equals 0. So you replace the f of x with a 0, and you get 2x squared plus 13x minus 24. And that turns the function into an equation, and you solve, whichever way you can. Now, what does that mean on the graph of the function? Where is it that the function equals 0? Yeah, the f of x, remember, f of x equals the y coordinate, right? And on the x-axis, y equals 0. So if you want to know where does the function have a 0, you look for the x-intercepts. On this function, where are they? Here, right? In terms of the graph, one is there and one is there. Okay, now how would we solve it? Without the graph, how would you solve that quadratic equation? I mean, you have choices, right? Is it factorable? Let's see, can you think of the factors of negative 48 that add up to 13? Off the top of my head, I can't. Okay, what else could I do? Quadratic formula. You know, just plug it in the quadratic formula. X equals negative 13 plus or minus the square root of 13 squared minus 4 times 2 times negative 24. Okay, which all over 2 times 2. X equals negative 13 plus or minus. Okay, this negative times negative is going to make that a positive. So it'll be 4 times 2 is 8. 8 times 24 is 192, right? So we've got 192 and 169. What is that? $11, 16, 361. And I don't know whether that, let's see, I'll use my calculator. Let's try second quit. Negative 13 plus second square root 361 divided by 4. Oh, 1.5. So let's look at our graph. 1.5. right? You could do the other one. Looks like it'll be 1, 2, 3, 4, 5, 6, 7, 8. I guess the 361 had a perfect square, and it was, let's see, that's not what I'm familiar with. Since that was 6, oh, it must have been negative 13, 14 plus 19. So that was the square root of 19 there. Find the zeros. I mean, looking at the graph, where's the 0? It looks like it's a 2. Again, if we were to solve it, it would be 0 equals the square root of t minus 2. So it's a radical equation. How do you solve a radical equation like that? First you isolate the radical, then you undo the radical. In this case, it's a square root, so you square both sides. What do you get when you square 0? 0. And what do you get when you square the square root of t minus 2? T minus 2. T equals 2. Zach, Duhan, head up. Okay. How about this one? Find the zeros. Obviously, I can look in the graph. There's the zeros. Let me substitute. 0 equals x squared minus 2 over x minus 1. How do I find the zeros for that? Should 1 be a 0? 1 is not a 0. What is 1? The vertical asymptote, right? Because what happens if you plug in x equals 1? You're dividing by 0, right? You can't do that. Remember, when you have a fraction equals 0, if I have a over b equals 0, that means the numerator equals 0, right? It's not coming from the denominator. It's got nothing to do with it. All you need to do is set the numerator equal to 0 and solve. Right, so x squared minus 2 equals 0. X squared equals 2. X equals plus or minus the square root of 2, which is about 1.4. Oh. So notice on the graph, you know, this is zoomed in. Between 1 and 2, a little closer to the 1, 1.4. Between -1 and -2, a little closer to the -1, -1.4. But don't think it's coming from the denominator. It's not coming from the denominator. If the denominator equals 0, it's undefined. It's only when the numerator equals 0 that the fraction equals 0. Good to go. Okay, Courtney. Okay. Ariana. Okay, next concept, like I said, this is kind of a hodgepodge of different concepts here, is increasing and decreasing. Right? Increasing and decreasing. So what we mean by increasing and decreasing is whether the y values are increasing as you go from left to right, or are they decreasing as you look from left to right? Like in this piece, look at this here. We can assume that this point, is directly over the -2. From x equals -2 to x equals 0, the y values are going down. So you would say the function is decreasing. Right? From 2 to the right, the y values are going up. They're increasing. So the function is increasing. In the middle here, they've drawn a straight line. It's a horizontal line. It's not increasing or decreasing. It's constant. So this is a decreasing. This is a constant. That's an increasing. The important thing and where we make the most mistakes with this is that when you're asked for an interval of increasing and decreasing, we're talking about the x values, right? They're intervals of x. So for example, here, I would say that the interval of decreasing is from -2 to 0, right? So I would write that like -2, and since it's got an endpoint there, I'll 0. It's hard to tell what goes on beyond that, but -2 to 0. Don't use 4 and 1. Those are the y values. It's true, the function goes from y equals 4 to y equals 1. But when you're asked for the interval, it means intervals of x. Okay. So what would you say is this interval of increasing? From 2 to 4, which the y values are going from 1 to 4, but this interval is 2 to 4. So don't give y values, Pierce. What if it's a vertical line? What is the title of our lesson today? Graphs of functions. Vertical lines aren't functions. I mean, if you tried to, he's saying, what would you say for a vertical line? Okay. And I said, well, it's not a function, so I don't have to answer the question. But if you look at a vertical line and try to apply my word definition there, is the graph increasing or decreasing as it goes from left to right? It's not going from left to right. It's kind of hard to apply that definition. It's not going from left to right. Right? So.
Like a little bit of an off-topic question. If a vertical line isn't a function, what is it?
It's a relation. Remember? Functions are relations that meet certain criteria. So if it doesn't meet the criteria, it's still a relation. Okay, so let's see on this one here. This is f of x equals x to the third. And you can see the function. This goes on forever, right? Like that. What you say is first, what is it doing? Is it increasing or decreasing? Increasing, right? The y values are going up from left to right. And it's going infinitely to the left and infinitely to the right. So you would say that it's increasing. What's the interval? -infinity to +infinity. And it's never decreasing. How about this one? What's it doing from here to here? And from here to here? And from here to here? Increasing, right? So if we wanted to write this interval, how would I write it? That's an increase, and it is -infinity to -1. Right? It's the x value, not the y, just the x value, to -1. And before I put in the last bracket, let's try to name this interval here. Right? This is an interval of decreasing. And where does it start? At -1, and it goes until 1. Okay, at the endpoints, it can't be both increasing and decreasing. In fact, it's increasing until it gets to this point, and then it's not doing either. So you would not call that a square bracket. It would be a round bracket. Right at the point, it's changing direction, so it's not increasing or decreasing. And then what would be this interval of increasing? 1 to +infinity. Okay, how about this one? This is a graph of a piecewise, right? It has 3 parts. There's 3 parts. Increasing, constant, decreasing. So what is this interval, which they don't have an endpoint like they did in the last slide. So you can assume that that arrow goes on forever. So you would say that that is an increasing from -infinity to 0, and they definitely included the point, so we'll include the point. And this is a decreasing. That's a decreasing starting at 2 and going to +infinity. Okay. So increasing, decreasing. Always give x values, right? Don't get confused with the y values. It's where you're most likely to make the mistake. Okay, when it comes to what they call relative maxima and relative minima, we're going to define what they are. There's really only one kind of function that we can do reliably that we could always tell what the relative maximum or minimum is. For the most part, it's a calculator function for us in this class. But when you get to calculus, it's like something you do right early on. You learn how you could algebraically actually figure out those points. Right? You take a derivative, you set it to 0, you solve for x. There you go. You got all the points where it changes direction. But by relative minimum and maximum, what we mean is it's not the absolute minimum or maximum. I mean, this graph, assuming that this graph goes on forever this way, let's say, that point there is not the maximum value on the graph, right? Because it goes higher over there. But it's the highest point in its vicinity, right? If I go a little bit to the left, it's less. If I go a little bit to the right, it's less. That's why it's relative maximum. Same goes with that point right there. It's a relative maximum, not the absolute maximum. Okay, and these 2 points are relative minimums. If this graph goes on forever, then clearly there's lesser values on the graph. Now there's one kind of function that we could always find it. We have algebraic means to find that. Do you know what that is? How about a parabola? Right? What point is that on a parabola? What do you call it? It's the vertex. Didn't we have ways to find the vertex? If you remember, the vertex, we used the letters HK for a vertex of a parabola. And we had a formula for the H. The H was negative b over 2a. So you just need to look, here's the quadratic function, plug in negative 4 for b and 3 for a. And you can calculate the H. So let's see. H equals negative 4 divided by 2 times 3, which is 4 over 6, which is 2/3. Now, that's the x value where that is occurring. Is that the actual maximum or minimum? No. The minimum value, since this one is opening up, will be what you get when you plug that in here. So plug it in. So the k is f of 2/3, which is 3 times 2/3 squared minus 4 times 2/3 minus 2. So that is 3 times 4/9 minus 8/3 minus 2, which is 12/9 minus 24/9 minus 18/9. So what is that? Negative 12, negative 39. So that's a little bit more than negative 3. So let's see. 1, 2, 3. It's about right. So that the minimum point on this graph is 2/3 negative 39. Oh, I could simplify that. Negative 10/3. So, but that's the only one that we actually have a way to solve for it right now. So you'll learn all about that in calculus. But we should understand what we mean by relative minimum and relative maximum. And then you could see this is decreasing from negative infinity to 2/3, and it's increasing from 2/3 to infinity. Okay. What is the range? greater than or equal to negative 10/3, right? It goes down as low as that, and then it goes back up again. Okay, rate of change, right? Average rate of change. If you have a straight line, by rate of change, you mean the slope, right? So the rate of change for a linear function is the slope. It's telling you how much the y is changing for how much the x is changing. Well, we're not doing linear functions. We're doing functions that actually have a changing slope. Like this graph, you can see it's increasing to a certain point, which means it would have a positive slope. It's decreasing after a certain point, which means it has a negative slope. Presumably, it has a slope of 0 somewhere in the middle, but there's not like one number you could put on it and know that. What you could do, though, if you wanted to know the average slope between two x values, is you could just connect those two with a line and then find the slope of that line. That would be the average rate of change. Right? Draw the line that goes through your two endpoints and calculate the slope of the line using a slope formula. When a line, this is geometry speak, when the line crosses, that's called a secant line. If it just touches in one point and keeps going, that's called a tangent line. You had that in geometry. But so you draw the secant line, the straight line that goes through these 2 points, and then you calculate the slope. In that case, the slope, I'll say this m secant. The y2 minus y1 now will be f of x2 minus f of x1. And the x2 minus x1 is x2 minus x1. And that will be the average rate of change. Yeah, if I drew a line like this, that's a tangent line, right? Because it just touches in one spot and goes off. But when it crosses, that's called a secant. You don't remember that from geometry? You don't remember that from geometry? Okay. It's called. Right. We don't really care about the tangent line here. Somebody just asked. You okay? Cheers. Okay. So if we wanted to find the average rate of change for a function, they got to give you the x values, right? And this one they're saying between x is -2 and x is 0. I mean, if I'm looking at the graph on a graph, so -2 is here and the 0 is here. So it's going to be the left point is going to be our x1, y1. So this is our x1. And this, because it's to the right, that's our x2. Now, we need to find f of x1 and f of x2. How do I find f of x1? Right, x1 is -2, so that would be, that's wrong. F of -2, which is -2 squared plus 2 times -2, which is 0. How about f of x2? Well, plug in f of 0, and we're going to get 0 squared plus 2 times 0, which is 0. So our formula would say the average rate of change should be f of x2 minus f of x1 over x2 minus x1, which is 0 minus 0 over 0 minus negative 2, which is 0 over 2, which is 0. So between those 2 points, the average rate of change is 0, meaning that secant line was a horizontal line. So if the function, just a second. Okay, Angelina? Okay. If the function happens to be a function which is distance as a function of time, something like this, s of t. The s is a position function usually. So when you plug in for the t, it's telling you how far did something go. Then when you have that kind of function, then the average rate of change is actually the speed. So there are some problems they say, find the speed of something, and it just means the average rate of change. It's the same thing. So since this is position as a function of time, or distance as a function of time, then the average rate of change equals the average speed. Probably you get this in physics, if you had physics. Does anybody have physics this year? You do? Yeah. Ariana? New physics teacher this year. So we're not going to do this one. I just wanted to make the point. Average rate of change equals speed. It just means you got a particular kind of function. Okay, and the last concept here, even and odd functions. What we call an even function means that if you graph it, it's symmetric with respect to the y-axis. Right? Well, something like absolute value. Right? That's symmetric with respect to the y-axis, right? It's like a mirror image on the right as it is the left. What it means is, it doesn't matter whether I take f of x, or if I go the same distance to the left would be f of negative x, both of them have the same y value. F of negative x equals f of x. You know, as long as you're going the same distance to the left and to the right, the function has the same value because it's symmetric. So odd functions are symmetric, and this one's a little harder to see, but we'll see it on the next slide. Odd functions are symmetric with the origin. Okay, and the test that we use is f of negative x equals negative f of x. Meaning if I have a function like, well, even like a straight line like this. So here's my x, right? F of x is this. But negative x would be the same distance to this side. And the value of the function is the opposite of this one. It says that's f of x. This is negative f of x. Right? The y value is flipped. So generally what we do, because there are problems where we have to determine whether it's even or odd. You plug in negative x for x, make it f of negative x, and see what happens. If it simplifies and what you get is the same thing you started with, then it's even. If you get the opposite of what you started with, then it's odd. And if you get neither, then it's neither. Now, one thing about an odd function, just to be clear, an odd function's got to go through the origin. It has to go through the origin. So let's see. Let's look at the even one first, because that's the easy one. Here's a quadratic, x squared plus 1. We know it's opening up. It has a y-intercept of 1. And because of what we know about parabolas, it's symmetric with respect to the y-axis. It's the same to the right as it is to the left. They're just mirror images of each other, right? Which means that if I go f of 1 would be here, f of negative 1 is the same place. That's even, right? This is what we call odd, symmetric with respect to the origin. Again, it's got to go through the origin. And notice for f of x, I get this point, this y value. If I go the same distance to the other side, f of negative x, then I get the opposite of what I got when I did that. That's what that f of negative x equals negative f of x, right? That's what that means. So basically, you're always kind of like, your graph is like opposite quadrants. If it's got a point here in the first quadrant, it's got to have a mirror image down here in the third quadrant. Right? If it has a point here in the second quadrant, it must have a mirror image down here in the fourth. For every point you see there, there's another one there. Even and odd. So determine if it's even, odd, or neither. Okay. So again, the test that we're going to do now is we're going to go f of negative x. How do we find f of negative x? Say again? Well, how do I find f of anything? F of 2, I would substitute 2. F of x plus h, I would put in x plus h. F of negative x, put in negative x, right? So this becomes 5 minus 3 times negative x. Simplify. 5 plus 3x. Now, is that exactly that? So it's not even. It would have to be exactly that to be even, so it's not even. Is it exactly the opposite of that? Well, let's see. The 3x, negative 3x is good, but the 5s are the same. So this does not equal f of x, and does not equal negative f of x. So it's not even, it's not odd, it's neither. Try the same thing with this one. Determine whether it's even, odd, or neither, which means find g of negative x. What am I going to do with the negative x? Substitute it for x. Negative x to the fourth minus negative x squared minus 1. Well, what is negative 1 to the fourth power? Positive 1, right? Whenever you raise negative 1 to an even power, you get 1. So this whole term, negative x to the fourth power, is x to the fourth. How about negative x squared? It's positive x squared, right? The negative squared makes positive. So that's minus x squared, and the minus 1 stays the same. Okay? That's equal to the function we started with. What kind of function is it? It's even. That equals the g of x, so this is even. Courtney, good? Okay, one more time. So to determine whether it's even, odd, or neither, we'll do h of negative x, which will be 2 times negative x to the third power plus 3 times negative x. So what do you get if you have negative 1 to the third power? negative 1, right? It means this term is like negative 2x to the third. And 3 times negative x is minus 3x. Now, if I factor out the negative, that's negative 2x to the third plus 3x. So I got exactly the opposite of the function I started with. Right? That equals negative h of x. Right? It's the opposite of this. So what is it? It's odd. If you recognize it, it's okay. Nope. Okay. Even a nod. I think that's the end. So we did vertical line test, zeros, increasing and decreasing, relative maximum and minimum, average rate of change, even and odd.